So welcome to Climate Central's monthly climate brief. Climate Central is a nonprofit, non-advocacy organization of scientists, communicators dedicated to researching, reporting, and storytelling around the data and the science of our changing climate. At Climate Central, we develop and distribute broadcast and publish-ready climate content, as well as data for you to help empower your forecasts, your stories, and your decision-making to make the crucial links between extreme weather events and human-caused climate change. I'm Jen Brady. I'm going to help moderate and handle some of the questions and answers for our speakers today. So please use that question and answer box. This month, we're going to look back at 2025. We'll review the climate and weather statistics for the year, as well as December statistics. Also joining us this month is Adam Smith to discuss the $2025 billion disasters tally. Throughout the webinar, we will be taking questions in the question and answer box. So make sure you use the box. That's where we're going to be looking for the questions, and that's where we're going to pull them up. All questions are also going to be answered after the presentations are finished. So we're going to wait until both speakers are done before we answer our questions. So now on to our discussion. Leading our discussion is Dr. Zach Leib. Zach's interests explore the intersection of climate impacts, future scenarios, extreme events, early warning predictions, and applying novel data science methods like machine learning. In addition to these research areas, he is very passionate about improving science communication and data-driven visualizations, and has an excellent social posting if you want to follow him separately. Zach was a scientist at NOAA's GFDL before joining Climate Central last spring. So welcome, Zach, and go ahead and get us started.
All right. Thanks for the introduction, Jen, and thanks everyone for joining today. I'm really excited to chat with you all about the recent climate statistics and data from 2025, and most recently also in December 2025. So I just want to point out before we get started, as was mentioned, this is part of a new webinar series that we're starting here at Climate Central. In addition to the webinar, which will be recorded, so there will be a video available from all of today's presentation, there is also a website page where you can go and find a report on the latest climate data and statistics, as well as different graphics and visualizations that you can look at and use for your own work to talk about the recent climate that we are seeing around our planet. So I recommend you check out our page. We also have the upcoming webinar schedule posted through May for the next briefings. And so we'll get started by jumping right into the statistics and data from 2025. So here's a look at global temperature for every single year from 1850 all the way through 2025. So this is showing the temperatures compared to a pre-industrial average. So what that means is each year is compared to the average temperature back from 1850 to 1900. So each little bar is every single year. So the blue bars were the colder than average years, and the red bars are warmer than average years. So you can see that there is, of course, a long-term warming trend. And 2025 was the third warmest year on record in this data set from NOAA. This was, in the NOAA data set, about 1.3 degrees Celsius above the pre-industrial average, although there are some variations between different statistical methods. As you can see here again, there's year-to-year variability, but a clear long-term trend, especially in recent years where we've seen such anomalous global warmth. And so where does that fit? If we look at the 10 warmest years in our record, they have all fallen since 2015. So there we are here, highlighted the third, where the first warmest was last year and the second warmest was 2023. So the three warmest years are within the last 3 years. And what does that mean for you? All of this global warmth relates to increasing numbers of extremes, and all of those relate to high impact events. So this increasing global warmth that we're seeing due to human-caused climate change is causing greater heat waves, more intense precipitation, heavy rainfall, other types of extreme storms, all increasing risk and impacts to communities around our planet. And so if we break that down, so I previously showed you what the average global temperature was, but what does that look like on a map? What does that look like in your backyard? So this map is showing the temperatures compared to a recent normal. So anywhere in red on this map means that in 2025, your area was warmer than the last 30 years on average. Anywhere in blue was colder than that 30-year period. As you can see, there are a lot more reds than there are blues on this map. Some of the most unusual warmth was found within the Arctic. The Arctic is one of the fastest warming places on our planet, warming at a rate that's up to 4 times faster than the rate of the global temperature. But there were also extremes and unusual warmth in many other places, including parts of Europe and parts of Asia, which saw temperatures more than 3 to 4 degrees above just the recent 30 years. Again, on average, our planet was the third warmest on record, but we also saw increasing high temperatures over the global land and global ocean, which was also the third warmest. In addition to air temperature, which is what you're seeing on this map, 2025 also set a new record high for the global ocean heat content. As a reminder, more than 90% of heat is absorbed into our oceans, so it's a real clear indicator of our warming planet. And again, both in the upper ocean and the deep ocean, we set new record highs for total global ocean heat content in the last year, consistent with our long-term trend. Another way we can look at 2025 temperatures is not just how they were compared to the recent 30 years, but how did they fall within the past historical record? So this map is showing temperatures again for 2025, but they're ranking. So anywhere in the darkest red boxes, that's indicating that that area had its warmest year on record. So many parts of the world actually saw their warmest year on record. Again, parts of Asia and parts of Europe saw a very warm year, the warmest on record. Also, parts of the Western Pacific, it was incredibly warm. Overall, that global temperature warmth continued for all months of the year in 2025. In fact, 11 out of those 12 months had global temperatures rank in the top 3 warmest for that respective month. Interestingly, only December was the year that didn't fall within the top 3. It was the top 5, and I'll show graphics and data in just a few moments for looking at December's data. One of the real striking statistics, at least to me, is taking a look at temperatures over land. Of course, land is where we live. So these are temperatures that are directly impacting, again, communities all around the world. And if you average the temperature over land areas, 2025 was actually the second warmest year on record. So this graph is showing the average temperature over global land areas. On the left-hand side are years in 1900. On the right-hand side is showing most recently in 2025. So again, you can see in recent years, especially the last 30, 40 years, this long-term increasing trend, but really the remarkable warmth from 2023, 24, and 25. Again, to me, this is a real striking indicator showing how all of this global warmth is impacting us. Some other noteworthy statistics were if you break down the temperature, just looking at it over different continents, it was the third warmest year on record in 2025 across Asia, and Europe was statistically tied for the second warmest year. So many different parts of the world also observed a very warm year. All of this, again, consistent with the long-term warming trend that we've seen, particularly striking in the last 40 some years. So what about precipitation? So we've seen that it was a very warm year around our planet in 2025. What does this mean for precipitation? So this map is showing precipitation compared to normal. That's again that word anomaly. So anywhere in green on this map means that it was a wetter than average year, more precipitation compared to normal in 2025. Anywhere in brown was a drier than normal year. So as you can see, there were particularly large deviations in the amount of precipitation over parts of the tropical regions. This is very much related to the La Niña pattern, which contributed to very wet conditions, such as parts of the Western Pacific, parts of Southeast Asia, which saw very wet conditions that included Northern Australia. We also had some very dry spots on our planet compared to normal. This included parts of the Amazon in South America, which were much drier than average in 2025. This also stretched out into parts of the Eastern and Central Pacific towards Hawaii, which saw a very drier than average year as drought conditions are continuing in that region. So again, this year was not just temperatures that were anomalous, but we also saw a number of different types of extreme precipitation anomalies around our planet. So again, just to ground us, what is driving these long-term trends that we're seeing in the data? And it's greenhouse gases. Greenhouse gases are these heat-trapping gases in our atmosphere. And as we increase them, they trap more and more heat. And this is due to the fossil fuel emissions that are human caused. So this graph is showing the latest data on carbon dioxide levels for every single month from 1958 all the way through present. This is data from Mauna Loa on Hawaii's observatory that gives us the infamous Keeling curve, if you're familiar with that term. This is showing the increasing rise of carbon dioxide, again, more heat trapping greenhouse gases. You can see the seasonal cycle, that's sort of the oscillation of plants and when they grow between the northern and southern hemisphere, but it's increasing over time. At its seasonal maximum in 2025, we passed for the first time in our historical record 430 parts per million. So what does that number mean for us? That just means more greenhouse gases, more warmth that is being trapped on our planet. And so we can see current CO2 levels are starting to rise. They're about 427 parts per million as of last month, and it's rising and will reach its next seasonal maximum, which is likely to set another record in May of this year. So there are other greenhouse gases in addition to carbon dioxide that also contribute to our planet's warming. So these graphs are showing some other contributors. So on the left-hand side, you can see changes in methane, and on the right-hand side, you can see changes in nitrous oxide. There's some variability and differences between the two graphs, but again, both of them show that we continue to see rising levels of greenhouse gases in addition to carbon dioxide as well. And all of this is contributing to this more heat and energy imbalance of our planet that is human-caused climate change. So what does this also mean in terms of approaching some of these thresholds that we often hear about for policy and for the news and understanding impacts? And one of them is related to this number that's 1.5 degrees Celsius above pre-industrial average. Really what that means is it's this threshold that we're getting closer and closer to that was outlined in the Paris Climate Agreement. While it's not necessarily some sort of magic number where the impacts get much worse as soon as you reach it, but it's this number that just shows that we're getting closer and closer, and more warming is increasing the number of impacts around our planet. And some of the latest predictions and models that look ahead to the next couple years highlight from the World Meteorological Organization that there's a 70% chance that the next 5-year average will have global temperatures at or more than 1.5 degrees. Again, any additional warming causes greater impacts to people around our planet. So I want to just really highlight that if you're interested in more of this climate change information, the causes of climate change, the solutions to climate change, to really check out this new resource we have from Climate Central of a free slide deck presentation that outlines graphics and information that you are welcome to use in your own science communication efforts. So in addition to human-caused climate change from things like greenhouse gases, we also have natural variations in the climate system that can temporarily accelerate or slow down global warmth just a little bit. And one of these phenomena in the climate system might be one that you're familiar with hearing a lot about on the news, and that's El Niño and La Niña. So I wanted to check in on the latest conditions for those. And this is an area, if you're not familiar with this, La Niña is a climate phenomena. It's found across the central Pacific Ocean, and it's associated with cooler than average sea surface temperatures, really stretching off the coast of Ecuador in South America and stretches across into the central Pacific Ocean. So we are currently in a La Niña phase. So that, again, that's the cooler sea surface temperatures. And why we monitor conditions in that region is these El Niños, which is the counter to La Niña. So El Niño is warmer than average in this area. This phenomenon can really impact weather and climate conditions elsewhere around our planet. It can also create or sort of temporarily accelerate global temperatures ever so slightly. So it can make the year even warmer during an El Nino year or slightly dampen the records a bit during La Nina years. So right now we're in this La Nina pattern. And one measure that we often look at to sort of quantify the strength of how strong this La Nina or El Nino is we measure ocean temperatures in one particular region. This region, if you're interested in the scientific jargon, it's called the Niño 3.4 region. It's this little area, again, off the coast of Ecuador, where they monitor sea surface temperatures and how they compare to average. So this graph is showing you how the sea surface temperatures oscillate over time. This graph is showing since 1950 all the way through present. So you can see it oscillates. There's stronger events. You can see some of those infamous stronger El Nino events, which related to lots of extreme weather conditions around our planet, such as in 2015, 2016, or the really strong one in 1997 to 1998. And then if you can compare where we are today at the very far right-hand side, you can see that we're in this very weak La Nina conditions right now. But the key word is for now, and that might be changing. So as I mentioned, in addition to affecting regional weather conditions, it also can affect global temperatures. Again, usually La Nina conditions are associated with slightly cooler global temperatures relative to El Nino years. So this graph is trying to really break down the influence of both the long-term trend and these natural oscillations. So there's very tiny little bars on this map or this plot of temperatures. Each bar here is showing one single month, and it's color coordinated by whether it's an El Nino year, a neutral year, or a La Nina year. So really, to me, the real striking takeaway here, of course, is there you see the long-term trend due to human-caused climate change, but there's lots of variability along the way. But I think what's so striking to me as a climate scientist is that if we look at 2025, which again is this weak La Nina year, which should be associated with slightly cooler global temperatures, but because of the human-caused climate change signal, 2025 was even warmer than the major El Nino years just from recently in 2015 and 2016. Again, showing how much our planet is accumulating warmth and relating that to more and more extreme weather and high impacts. So what do we look like going forward into 2026? So what you're looking at here is a map from the NOAA Climate Prediction Center, where the bars graphs here is showing the probability of different conditions for El Nino and La Nina for the next couple months going forward into the future. So anywhere you see sort of the blue bar really high, that's showing it's more likely to be a La Nina. Anywhere the gray bar is showing more likely to be neutral conditions, and the red bar is showing more likely to be El Nino. So really here, what you can see is that we're slowly moving away from La Nina conditions and moving towards neutral and maybe even a weak El Nino by the end of summer this year. It's important to point out, though, that the statistical models and the physical models that we use to predict it, and so have their own uncertainties. So there are some uncertainties related to this forecast, but it does appear a growing likelihood that we will be transitioning away from this La Nina into warmer conditions across the Central Pacific, lining up that 2026 and maybe 2027 could be quite warm years for global temperatures. So if we want to step out further and look at the rest of ocean temperatures, on the left-hand side is showing sea surface temperatures. So that's the ocean surface and how they compare to normal as of December. So anywhere again in red was warmer than average ocean temperatures. Anywhere in blue is colder than average temperatures. So you can really see that La Nina signal there in the Central Pacific, but really the remarkable warmth occurring across much of the mid-latitude regions in both hemispheres. So we've been seeing large marine heat waves across parts of the North Pacific. We've been seeing them around New Zealand and Australia. Again, these really remarkable warmth impacting marine ecosystems, in particular in this region. So now let's take a look at what the US was looking like during 2025. So for the US, this graph is showing the 10 hottest years on record. So 2025 was the fourth warmest year on record for the United States. Again, warming temperatures, more extreme weather, rising impacts affecting communities. Last year was actually, or 2024 was actually the warmest year for the US. So again, consistent with recent years being unusually warm. And so now let's take a look at what does that look like in your backyard. So on the left-hand side is showing a map across the lower 48 for how temperatures compared to average. So again, anywhere in red is warmer than average, blue is colder than average. So you can see pretty much every location across the US was warmer than the average from the 20th century. On the right-hand side is showing just a bar graph of each of those individual years since around 1895 on the left to present. You can see there's that year-to-year variability. Not every year is going to be a new record, but there's a clear long-term trend due to, again, climate change. So what about the rest of the US? So taking a look at Alaska, Alaska was the ninth warmest year on record. So on the left-hand side, you can see that temperatures across much of Alaska were much above average when you rank them over the historical record. Hawaii was also warmer than average, but not quite as noteworthy for temperatures. However, as I mentioned earlier, it was a very dry year in Hawaii with drought conditions across many of the islands. So that was a particularly noteworthy anomaly over Hawaii in 2025. So taking a look now, instead of looking at the anomaly or how the temperature compared to average, how does it rank when we look at the entire historical record? So you can see many areas for 2025, if you look at that dark red color, many areas across the West had their warmest year on record. States across like in Nevada, in Utah, and parts of Arizona had a record warm year. And the less extreme temperatures, or at least in terms of the ranking, were found across parts of the eastern and northeastern United States. It was also a very warm year for the average daytime temperature, so those high temperatures in the afternoon, as well as nighttime overnight low temperatures. For precipitation, it's been a pretty dry year across the United States, ranking in the driest third of the sort of long-term record that's 131 years long. So this map is showing, where those different extremes were. It's important to recognize there was also a lot of variation depending on the month for these extremes. So it started off quite dry across the western United States in 2025, later becoming very wet across the West. However, on the other hand, for parts of the eastern United States, it was much wetter than average, sort of earlier in the year, especially in the spring and early summer when there were many flash floods across the country, and then has become increasingly dry during the fall and early winter across parts of the southern US and eastern United States. So a map like this doesn't tell the full story necessarily of precipitation. So what about more recently in 2025? Let's take a look at global temperatures now for December. So we're going back to those maps where red is warmer than average, blue is colder than average. So if we just look at the last month in December, you can see some really striking temperature departures across the Northern Hemisphere in particular. If you zoom in sort of to North America, you can see that it was really, really warmer than average across sort of the Western United States, but significantly colder than average across parts of Alaska, stretching down into Canada and parts of the Northeastern United States. So really those darker colors indicating a really sharp contrast in temperatures from a very amplified jet stream contributing to that sort of weather pattern. We also saw that very consistent over parts of Asia, where parts of Siberia were much colder than average, while warmth was stretching across much of Asia during the month of December. So again, focusing on, like I said, in December for North America, had those real sharp contrasts depending on where you lived for temperatures. So we can see that that contrast contributed to temperatures across North America actually being pretty close to the recent 30-year average. Again, as a reminder, there is year-to-year variability in temperatures. It's the long-term trend that we always focus on in climate. But again, those records were really remarkable in some locations, such as parts of Greenland, observed their warmest December on record. So it was very much dependent on where you were located, where we saw those sharp temperature departures in the month of December. So focusing in and zooming in on sort of the United States back in December, this was an area where we saw the really amplified pattern, this big ridge of high pressure across the west that contributed to really warm temperatures across the western United States. Here, anywhere in that dark red shading is indicating that that location had their warmest December on record, so stretch across many states in the western US, while those colder temperatures were mainly found across the northeast United States, anywhere from sort of eastern North Carolina all the way up through Maine, so colder than average temperatures during the month of December. But overall, across the lower 48, temperatures were still the fifth warmest year on average for the month of December. In fact, 9 states actually observed their warmest December all across the western United States. So that stretched anywhere from along the entire Pacific coast all the way into the Rocky Mountains, where there's been a huge snow deficit also in these areas. So parts of anywhere stretching from Nevada, Utah, Colorado, into New Mexico have all seen very warm temperatures so far this winter and very much a lack of snow, which could have big implications for water resources as these areas rely on a snowpack building during the wintertime to then melt out in spring, contributing to water levels. So this will be something we're really focusing and keeping an eye on closely through the rest of winter to see if snow conditions and average temperatures change moving forward into February for these areas. And I just want to point out that no states, despite, may feel cold. I'm located here in Pennsylvania. It's pretty cold out today. No states observed their coldest December on record. And so if you average all temperatures across the contiguous United States from 1900 on the left all the way through 2025 on the right, you can see that's what the yellow line is showing for each individual year. Lots of year-to-year variability, but there is that long-term trend increasing over time. And this is a reminder, as it's cold and snowy and we're all talking about a potential winter storm to impact the southern and eastern United States, just to recognize that even in a warming climate, we will continue to see periods of cold, periods of snow. Sometimes it will be really, really cold and big in snow. And that's because we're seeing our distribution of temperatures shift to the right. So that's what you're seeing by this graphic. So there will still be cold temperatures, but they're going to be less and less common. So we'll see an increasing chance for really warm winter days rather than really cold winter days with more and more climate change. But that doesn't mean it's still not going to snow and feel really wintry outside at times. It will probably just occur less and less into the future. One state that was very cold in the month of December, as shown earlier, was in Alaska. It was actually the 11th coldest December on record, the coldest December for the state of Alaska since 1980. And it was the first time the average temperature for the whole state was below zero in over 5 years. So December had a very cold and very snowy, if you were in parts of southeastern Alaska, month of December. For precipitation, we can see that it was very wet across the Pacific Northwest in December, and much of this related to a series of atmospheric rivers, which brought record-breaking rainfall across parts of the Pacific Northwest into Washington, parts of Idaho, and western Montana. But it was very dry across much of the southern and sort of eastern United States. This dryness has continued to be a common pattern for the last couple months from into the fall. So if we take a look at conditions in terms of the drought monitor across the United States, anywhere in yellow into those orange and red colors means that either your area is abnormally dry or it's actually into moderate to severe droughts. So you can see actually much of the contiguous United States is very dry right now. This is especially prevalent along the east coast of the United States from Maine south into Florida, stretching across into parts of Texas, which are in areas of extreme drought. One very noteworthy exception, where an area that very much in these maps before was highlighted in drought, is California. California is actually drought-free for the first time since December 2000. So that is actually one state that is not observing, at least at the moment, these abnormally dry conditions. And that's very much in part to the series of atmospheric rivers that brought a lot of heavy rainfall and flash flooding to much of the state during the month of December. So we will see how that turns out for the rest of their water season during the winter time. So just want to final check in quickly on what is the temperatures and precipitation outlook look like for the next couple of weeks. So it's likely we're going to see sort of a very similar pattern occurring where you're seeing colder than average temperatures, or more likely for colder than average temperatures across parts of the northern, northeastern United States, in that warmth continuing across the western United States, with the most likely probability being really in the southwest area. For precipitation, we're seeing a slight signal for potential for more dry conditions across the Northeast and wetter conditions to be more likely to occur across the Pacific Northwest. So very much the pattern over the next couple of weeks looks very much of what we've been seeing throughout much of this winter. And so really in summary for our briefing for 2025 and most recently in December is that global warmth is persisting. 2025 ranked as the third warmest year on record, even with the weak La Niña conditions. This warmth was also found across the United States, where nearly all areas were warmer than the 20th century average. Conditions have also been quite dry across the US, accompanied with this warmth. It doesn't mean that everywhere is dry, as we've shown there's been exceptions, like in the Pacific Northwest with severe flooding so far this winter. But it looks like this general pattern is expected to continue through at least the end of January. And as far as El Nino and La Nina, it's more likely that the La Nina will begin to wane potentially very quickly, given some of the projections, with a tendency for us to trend towards neutral or maybe even weak El Nino conditions. And so I'll just highlight that our next briefing on climate conditions is coming up in February, and we are expecting a special guest on a topic to talk about changes in extremes, particularly for the jet stream. But until then, we will now turn it over to our next topic, which will be on a review of billion-dollar disasters in the US. And I'm so excited to be joining us today is Adam Smith, Senior Climate Impact Scientist at Climate Central. Adam has been the lead researcher and developer of the billion-dollar data disaster set for over a decade at NOAA, and he now is bringing this and relaunching it here at Climate Central. Adam's work is really leading the way in understanding how natural hazards and disasters are changing across the United States, combined with changes in things like exposure and vulnerability, which impact cost estimates and why we're seeing rising costs from these disasters across the United States. So today he'll be reviewing 2025's billion-dollar disasters, as well as some of the new and exciting ongoing research we have at Climate Central on this topic. So I will turn it over to Adam, and you can take it away.
Thank you, Zach. So yes, today I'd like to highlight 2025 into historical context and what we've seen in terms of extremes, how that's changed over time, what are some of the drivers, and wrap it up with some exciting new work that we're doing this year to expand the scope and the depth of this historic data set. Next slide, please. So at Climate Central is really a gold standard nonprofit in communicating climate change science, the effects, the solutions to many different end users for many different products. And part of that is tracking the trends and impacts of extremes. And so the U.S. billion-dollar disaster is, one of those data sets that is kind of the gold standard in terms of the best public and private sector data partners, methods to expound and show how these extremes are changing over space and time, and the multiple drivers for why we are seeing increased costs. So this data set began in January of 1980, and our last analysis was through December of 2025. And throughout that 46-year period of record, we've identified 426 separate weather and climate extreme events across the nation that have inflation-adjusted billion-dollar disaster impacts. In fact, 68 of those 426 events are actually below $1 billion, but in today's dollars are $1 billion or more in damage. And yes, this is an arbitrary threshold, but historically it has a bit of a signal because it represents about 80% of the full cost distribution for these weather and climate extremes at all scales and loss levels. Next slide, please. So as I mentioned, as Zach mentioned, we're literally continuing and relaunching this data that has long been at NOAA, using the same best public and private sector partners and data sources to capture total direct losses. So this chart briefly summarizes how some of our core partners work with us, including the insurance reinsurance industry, FEMA, USDA, parts of NOAA, of course, like the Storm Prediction Center, Storm Data, even the National Interagency Fire Center, Energy Information Administration, and U.S. Army Corps of Engineers. And the X's denote the intersections between those partners and their data sources and the different hazard types at the top that we've assessed historically. And I think the bottom of this slide is really critically important. From all of this data, we're capturing 16 different asset classes across all these different hazard types, including insured and uninsured losses to homes, businesses, government buildings, not only the physical structures, but even the contents of those structures, and time element losses, like when you're out of your home or your business while it's being repaired. Also, damage to vehicles, boats, offshore energy platforms in the Gulf of Mexico when hurricanes are coming through. Damage to public infrastructure, roads, bridges, levee systems, electrical grids, even lack of hydropower in the West when we have a long duration severe drought. And finally, agricultural and forestry losses, such as damage to crops, livestock, commercial timber, and the wildfire fighting suppression costs. So those are kind of the 16 asset classes. But I think it's equally important to note what we are not capturing, including damage to natural capital or environmental degradation from these extremes, the mental and physical health care related costs after a disaster as people are recovering their lives and livelihoods. And finally, the supply chain ripple effects outside of the hazard region also are not captured. So even though it's a comprehensive estimate using the best available data back to 1980, it's still conservative with respect to what is truly lost but cannot be completely measured. Next slide, please. So here is 2025. It was really an interesting year. I can't quite recall a year like it in at least a decade because we start off fast and hot, unfortunately, with the LA wildfires, the costliest wildfire on record, 61 billion. And then we had a very active severe storm season from March through really July, early August. And then things slowed down and kind of stopped, which you'll see in the data. But so I guess it was really the LA wildfires was the historical anomaly, more than or basically doubling the inflation adjusted wildfire cost record last set back in 2018, also in California. But the severe convective storm events you can see throughout the central, southern, and southeastern parts of the nation really were the other story, which is many tornado outbreaks in the spring, several hail events you can see in Texas and in Colorado and the South as well, and then even a derecho that raked across the Northeast. In fact, blowing out windows in skyscrapers in downtown Pittsburgh in late April. So again, once again, we saw many parts of the nation have many impacts, and we're trying to learn from these events and better build a stronger, more resilient future. Next slide, please. So the red line in this chart shows the accumulation from January through December, the count, the frequency of these billion-dollar disasters across the nation. And you can see last year, 2025, was the third highest on record, only behind the years 2023 and 2024, as you can see at the top. The black line is the inflation-adjusted average, about 9 events per year, each year, 1980 to 2025. And so it was, this chart makes you think, we had a lot of events, we did, but other than the LA wildfires and then a mid-March tornado outbreak, they were really more small events from the $1 to $5 billion range in terms of the severe convective storms. Next slide, please. And you can kind of see that here in this data. This is showing the same setup, but instead of annual frequency of events is annual cost accumulation from January through December. Again, the red line was last year, and you can see it was in the top 10. I believe it was number 9, just behind, just barely trailing 2018. And that's because we didn't have landfalling hurricanes. It's been a decade since the United States was not impacted by a landfalling hurricane, and you can see how compared to other years in this chart, when you get into August, September, October, a lot of the lines for the more costly years certainly rise in terms of the cost, which you can see on the left y-axis. But we didn't have that in 2025, thankfully. In fact, I believe 6 out of the last 9 years we've had major landfalling hurricanes. So we were lucky and that we just were not impacted by any of the 3 Category 5 hurricanes that were generated in the Atlantic, which, as we know, the more powerful hurricanes, they certainly drive the loss of lives, livelihoods, and dollars. And you can see the leading years, 2017, 2005. Those were clearly hurricane years with Katrina, Rita, Wilma in 2005, and in 2017, Harvey, Irma, and Maria. So we can't forget those, of course. But yeah, last year was, as you can see, started off well above average. In fact, the fastest start all the way through July, and then just it got quiet. So next slide, please. But if you actually looked at that same data set, January through December, the cost accumulation for each of the last 46 years, inflation adjusted, and you look at all the years, but take out all the hurricane damage, all the tropical cyclone impacts, you actually see last year was the most costly year on record, which frankly surprised me when I did this analysis. And you can see by quite a big gap there. And that does show, of course, our growth and exposure, our vulnerability as more and more people move and build in harm's way, and often maybe aren't building to the standards that can mitigate all these damaging events. But just showing how 2025, for many parts of the country, for millions of people, was quite impactful. Next slide, please. So this chart is the time series showing all 426 events from 1980 through 2025, color-coded by hazard type. The black line is the 5-year cost average for each as it goes through the time series, and the red line with the spikes shows the annual costs. So again, you can see how 2017 and 2005 and the red line really stand out in terms of the cost. And 2025 was, the 9th out of 46 there at 115 billion for the 23 different billion-dollar disaster events. And you can see how they were largely loaded. 91% of the 23 different billion-dollar disasters were related to severe convective storm. The only two were wildfire and then the Western drought heat wave were the other two events. But I would be remiss to say that there were, of course, many flood events across the nation. They just didn't quite reach the billion-dollar level, but we will be providing more data on those flood events in the future, which I can highlight in the next in a few slides down the way here. The two flood events in particular that could have been billion-dollar disasters, but quite didn't make it, were the Texas flooding in around July 4th, which was very tragic. More than 100 people killed. That was about a $750 million event. And then the mid-December flooding in Washington State, we frankly didn't have enough data to make that assessment. So that's still kind of TBD in terms of the total cost of that mid-December flood event. So as we know, this data has a lot of movement in it as it develops, and we're always trying to capture the latest and best data to provide the analysis. Next slide, please. So to step it back a little bit, to look at the full period of record from 1980 through 2025, you can clearly see different regions, different states really stand out in terms of total cumulative cost for these different asset classes we've measured. Florida, Texas, Louisiana, California, all in excess of 300 billion for their impacts from all these different disasters. But you can, of course, see the South and the Southeast have also high impact events. And on our website, just as the NOAA website, you can dive into this data and explore it. That's the goal, and make it more interesting to kind of zoom in on your own region, your own level of interest. But I think with this map, in addition, you can see we have data for Puerto Rico, Guam, U.S. Virgin Islands, Alaska, and Hawaii. But one takeaway from this map is that Louisiana has a much smaller area, population, and GDP compared to either Texas, Florida, or California, but it's proportionally the same impact. And a lot of that, of course, is driven from tropical cyclone and severe convective storm and flood events. So next slide, please. And so as an example, if you go to our Climate Central billion-dollar disaster website, you could slice and dice the data for different metrics, for different time series, for different states. And this slide kind of shows what I was just mentioning. If you look at the last 10 complete years, because we don't have 2025 national GDP data yet, it's the data latency has affected that data. So if you look at the last 10 years of state level billion-dollar disaster costs versus state level GDP, you can see how, unfortunately, Louisiana, is at a high level in terms of averaging more than 5% of its GDP each year over the last 10 years, losing that effectively to these disasters. But you can see many other states also are in the 1 to 3 to 5% range as well. So these continuous disasters do have bottom line concurrent impacts that we need to track and better understand to measure and make adjustments where we can. Next slide, please. Also, looking full picture for the 426 separate billion-dollar weather and climate extremes with a cumulative cost of excess of 3.1 trillion. You can see how tropical cyclones are the most costly of these different hazard types we've historically tracked. Hurricanes, strong tropical storms account for roughly half of the losses, 1.6 trillion. They have the highest event average cost at 23.6 billion per landfalling hurricane or a strong tropical storm, and also have the highest death count at in excess of 7,000. Also, you can see circled severe convective storm events have the highest frequency count, which should not surprise people because severe convective storms happen throughout the year, every year. They also have quite a high cumulative cost total at 578 billion. But what does surprise people is the cost of drought. I don't have it circled, but drought, $381 billion from 33 separate multi-season long drought events over the last 46 years. And when a drought has a strong heat component like last year's 2025 drought did in the West, of course, we also get direct and indirect fatalities, and close to 5,000 for these events. So, but of course, all this data does show our increasing exposure, our vulnerability, and the fact that climate change is supercharging some of these extremes into billion-dollar disasters. Next slide, please. Here's a different breakdown showing the data by decade and by the last 5 years and last year, just comparative stats here. And, I've got a few boxes just showing how the 2000s decade versus the 2010s decade really had a ramp up in terms of the frequency of these billion-dollar disasters. Granted, a lot of them are on the smaller end, mostly severe convective storm events in the $1 to $3 billion range. $67 billion disasters in the 2000s, 131 separate billion-dollar disasters in the 2010s decade. And then the box to the right shows how this total direct losses across all those asset classes I mentioned, how that, of course, is escalating as we move forward in time, as you'd expect. But it's really been ramped up over the last decade in particular. Next slide, please. Here's kind of a climatological look at these different billion-dollar disasters by hazard and by month. And so the year, well, if you look at climatologically 1980 to 2025, it's kind of a tale of two seasons in terms of you have a lot of severe storm events and flood events in the spring months, March, April, May, into June, and then it flips. And then in the fall months, hurricane season begins. Tropical cyclones happen. Drought and wildfire can often, kind of really feed off each other, and both can really do a lot of the damage in the late summer or early fall time frame. And so, you could look at any of this data I've shown so far today by your own state. We even have risk mapping. You can look at sub-state information. And so, again, we're trying to provide this information to others to help them better understand their growing exposure, their risk, and how weather and climate extremes are changing in their backyard. Next slide, please. Here's another view of kind of that last data slide, but kind of in terms of the probability of any month, and this is for the whole nation, having a billion-dollar disaster in that month. And again, as you'd expect, you can see how March, April, May, June, when you have so many of these severe convective storm events, you have springtime flooding events, maybe even a late winter storm event, how you get a high potential for these concurrent disasters somewhere, sometimes overlapping around our nation. And shorter time intervals between these disasters result in compound disasters with cascading impacts, which certainly slows recovery time, makes it more difficult, more challenging to recover to your pre-disaster baseline. But so you can, of course, look at this for your own state or your own region and see how your state or region compares to others around the nation. Next slide, please. And finally, kind of showing how, again, because we're having a lot of these extremes, certainly in more recent years, the average amount of time between these billion-dollar disasters has been going down. In the 1980s, it used to be about 2.5, 3 months between these disasters. Now it's about 2 weeks or less. In fact, I think last year was about 10 days between each disaster, looking at the average start and stop time of these. So again, these increased frequency of these disasters are impactful to everyone, but potentially more impactful to vulnerable socioeconomic populations that might not have help recover physically, mentally, as a community, losing jobs, etc. So this information is multidimensional, and it's helpful to understand how your region or your state is changing as we move into the future. Next slide, please. So this is pretty exciting, I think. Actually, we're doing a number of projects this year at Climate Central that have been asked for several years by the research community and by others, which I think are very valid for us to pursue. And this is adding the scope and the depth to this historical data set. So first, between now and June 30th, that's when we're trying to have this finished, we're going down to the $100 million level. So a whole order of magnitude down in terms of capturing the small and medium-sized disasters, which will help users of this data and this website see how the risk profile really looks, not just the tail events and the extreme historical events, but more common events. And having more data is, of course, more helpful. Also, we would like to historically break out the severe convective storm in terms of their primary damage drivers, whether that's a tornado outbreak event, a hailstorm over a major metropolitan area, or a large, widespread hailstorm event, or a wind derecho event. And so, breaking out having that added granularity in the data set, I think would be helpful. Similarly, we would do that to wildfire events as well. Historically at NOAA, when this data set was there, we would analyze wildfire seasons and a kind of multi-state, multi-wildfire season scale impact, which was really too coarse for deep analysis. So I think we're breaking down the individual wildfires all the way back to 1980 down to the $100 million level is our goal. And finally, a lot of this new information and the historical information we have in the billion dollar disaster data set can hopefully feed into some of these other programs and projects that Climate Central has, including Climate Matters, Climate Local, Climate Shift Index, or event attribution studies.